In this video, we're going to talk about perfectly inelastic collisions, which are sometimes called completely inelastic collisions. A perfectly inelastic collision is one where the objects stick together. That's it. It's very simple. Let's take a look at an example of a perfect or completely inelastic collision. Oh, the suspense is killing me. What's going to happen? Oh, nice. Reverse. Wow. Here we have a 1.5 kilogram toy car traveling 2.5 meters per second that collides with a 1 kilogram toy car moving 1 meter per second. The cars are moving towards each other. What is the velocity of each car if the collision is perfectly inelastic? And how much kinetic energy was lost? Give me a second to draw this situation. Okay, so here we can see that the two objects are moving towards each other, and afterwards they've sort of collectively become one object or connected, maybe locked bumpers, or with the two toy cars there was some Velcro between them. And after the collision they moved to the right as one unit. So you would still use P naught equals P to solve for the conservation of momentum, but in the beginning you would have two separate momentums, m1 v1 naught plus m2 v2 naught. But at the end, instead of writing m1 v1 plus m2 v2, it might be better to think of the two as one object, m1 plus m2, and then multiply that by just a velocity v, and not labeling it 1 or 2, because basically the velocity of each object is equal, so they're all the same thing. You can call it just your final velocity v. Solving for v just means that you take the initial momentum and divide by the total mass, which in this case is going to give you 1.5 kilograms times 2.5 meters per second plus 1 kilogram. And then you would need to make this a negative 1 meter per second because it's moving to the left. And when you divide this by the total mass, you'd have 1.5 kilograms plus 1. And this is going to give you a velocity of 1.1 meters per second. The shared, and that would be positive to the right, the shared velocity of the two cars. Okay, now to figure out how much kinetic energy was lost, we look at the kinetic energy in the beginning, which would be half of mass 1 times the initial velocity squared plus half of mass 2 times its initial velocity squared, or half of 1.5 kilograms times 2.5 meters per second squared plus half of 1 kilogram times negative 1 meter per second squared. Of course, that negative gets canceled out when we square the 1, and you're going to get an initial total kinetic energy of 5.187. We'll call that 5.2 joules. And now to find the kinetic energy at the end, you could write 1/2 m1 v1 squared plus 1/2 m2 v2 squared. But here's a quick trick. Since you're going to have the same velocity in both, I'll write this out, 1 m1 v squared. Since you're going to have the same velocity in both, and the 1/2 is a shared term, you can actually just write this as 1/2 m1 plus m2 v squared. And if you can just sort of see how this would be the kinetic energy of one object at the end with the total mass, then you really don't have to write out the initial kinetic energies of both. You can just put that down. And this is going to give you half of 1.5 plus 1 is 2.5 kilograms times 1.1 meters per second squared. And that's going to give you a kinetic energy of 1.5 joules. So obviously we've lost some kinetic energy. To write down how much, you would just write delta K, change of kinetic energy, your final 1.5 joules minus your initial 5.2, and this would give you a decrease of 3.7 joules. Okay, so we found the velocity of the car. after the collision, and we found the total energy that was lost, 3.7 joules. Let's do another example. In this problem, Kid A, that should say 50 kilograms. Kid A, 50 kilograms, is running 5 meters per second with a beanbag when he collides with Kid B, unknown mass, who is at rest. The two kids move together with a velocity of 3 meters per second after the collision. How big is Kid B? What is the decrease of kinetic energy? All right, give me a second to draw this situation. Okay, so here we have Kid A and Kid B running into Kid B, and they move together as one kind of blobbed unit going 3 meters per second, and we're going to figure out how big Kid B is. So we'll do energy conservation again for this. P naught equals P. And in the beginning, you would only have momentum from the first kid, which we'll say MA VA naught. And at the end, you would be able to write this MA plus MB times V for the momentum of one thing. But we're going to find that in order to solve this problem, we have to get MB by itself. So to do that, it's probably a much better idea for us to distribute the velocity, so that instead of MA plus MB times V, we have MA times V plus MB times V. This is going to let us get MB by itself. So MA VA naught minus MAV equals MB times V, and then we divide by the velocity to get the mass of Kid B. All right, and you can factor out MA if you want to, so that this would be 50 kilograms times the initial velocity was 5. The final was 3. Divide that by 3 meters per second. So 50 times 2 over 3 is 33.3 forever kilograms. So that is the mass of Kid B. Okay, now to find the decrease of kinetic energy, you would say the kinetic energy in the beginning is half the mass of A times the initial velocity of A squared, but you wouldn't need kinetic energy for Kid B because he's at rest. And this would give you half of 50 kilograms times 5 meters per second squared, so 25 times 25, which is going to give you 625 joules. And now to find the kinetic energy at the end, here it probably would be a good idea to treat them as one object, MA plus MB times the final velocity squared. We don't need parentheses there, just because it's going to be faster to put in your calculator. So half of 50 plus 33 is 83.3 repeating kilograms times the final velocity of 3 meters per second squared. And half of 83.3 times 9 is 374.9 forever, so 375 joules of energy at the end. So the decrease of the energy, delta K, is just 625 minus 375, or 250 joules. So that's the energy loss. Let's do one more problem. A box of mass m moves right with a velocity of vi when it collides with a box of mass capital M at rest. If the collision is perfectly inelastic, what is the decrease in kinetic energy of the two-box system in terms of m and vi? What is the that should say m and vi. And what is the decrease in terms of ki? Okay, let me draw this situation. So occasionally the AP test likes to use VI and VF for momentum problems. We'll just go ahead and use that. Normally we use V naught and V, but we can do VI and VF for initial and final. To figure out what the decrease of kinetic energy is, I need to figure out what VF is going to be. And to do that, I would start with momentum conservation, so P naught equals P. And I would note that the momentum in the beginning is just m times VI, because the little m block is moving, but the big M block is not. Now, the momentum at the end, since they stick together in a perfectly inelastic collision, I would write this as little m plus big M times their shared final velocity, Vf. Now I'd be able to find the final velocity in terms of little m, capital M, and Vi. It would be little m Vi over little m plus big M. If this was a multiple choice question, you might see this as one of the options, like letter A or D, something like that. But what we're going to do is we're going to use this to figure out what the decrease of kinetic energy is, hopefully with these terms inside of it. So let me show you what I mean. The kinetic energy in the beginning is just 1/2 m Vi squared. Because the little m block is going with a velocity of Vi, I don't need to do anything with the capital M block for the initial kinetic energy. But the final kinetic energy is a little different. It's going to be 1/2 the total mass, m, plus capital M, times Vf squared. But I'll do this off to the side here. If I try to find the change, delta K, oh, sorry. If we're using I's and F's, I should call this Ki and Kf. I'm so sorry. Take it up with College Board. I would want to call this Kf minus Ki. So if I plug those two equations into each other, I'm going to get an answer, but it won't have Vi in for the final velocity. So what I need to do, and what the AP test would want me to do, is to replace Vf with that equation in terms of Vi. So what we get is 1/2 m plus m times m Vi over m plus m, the whole thing squared. Now I have to do a bunch of simplifying. When I square what's inside of my parentheses, I'm going to get m squared, Vi squared, and then the term on the bottom, m plus capital M, this would also get squared. Of course, this m plus capital M would cancel one of the m plus capital M squareds on the bottom, and so we would be left with 1/2 times m squared Vi squared. I'm going to put the half down here at the bottom of the 2, times m plus capital M. I know, it is just infuriating. Okay, well now to get an equation for the change of kinetic energy, I would take that new equation that I have for Kf, and I would write m squared Vi squared over 2 times lowercase m plus capital M, and then subtract 1/2 lowercase m Vi squared. Now, maybe it's not such a great idea to put the 2 on the bottom for this, because we're going to end up pretty much pulling it outside anyways, so that it's easier for me to see what happens. Pull the 1/2 out, 1/2. But effectively, you would pull the Vi squared out, and then you would get m squared over m plus m minus m, which annoyingly is an acceptable answer for a free response question that would ask you to find the decrease of kinetic energy with these terms. Now, what you could do, if you wanted to, was pull out 1m. So you'd get 1/2 m over m plus capital M minus 1. That might be one of the answers that you see in a multiple choice question. So you would have to kind of simplify it to get there. But if you wanted to get a decrease in terms of Ki, then basically you would rewrite this m plus little m over capital M minus 1 with the 1/2 m Vi squared over here, because this is your kinetic energy in the beginning. So you would have m over m capital M minus 1 times Ki. That would be also another possible choice on an AP multiple choice question, or perhaps a free response. Congratulations, you are done.